Hello and welcome to Unit 7, Part 6. My name is Mr. Bell, and today we're going to solve some quadratic word problems, and we're also going to identify and interpret key features from graphs and from different scenarios. Before we actually do an example of a quadratic word problem, I want to review some of the key features of quadratic functions on a graph. Now recall from previous lessons that when you graph a quadratic, it's going to make the shape of a parabola, which is either a sort of a U-type shape or like an N-type shape. A lot of times, quadratic word problems are involving something being thrown into the air or flying through the air, a rocket, a rock, a ball, an airplane, because on the planet that we live on, gravity is a factor when most things they go up. Unless there's a force or something propelling it to keep going up, it will eventually come down. So a lot of the quadratic word problems we're going to do are going to carry this shape on the graph. Okay, that is the shape of a parabola that opens downward. Now, I didn't draw a real great one, but let's look at some of the key parts and just see if we can remember. The very top, the very peak of the quadratic function, recall, was called a vertex. It consists of an x and a y value. And most of the time, not every time, but most of the time, the x value of the vertex represents the time. For instance, if you stepped across the x-axis here, this would be how many seconds it took to reach that maximum height. The y value is typically the maximum height, maybe like in feet or miles or inches. It just depends on the quadratic that we're talking about. So you're going to have to find the vertex from the quadratic that we graph and realize that each value, the x and the y, they carry some kind of meaning. A lot of times the x-intercepts or the roots are very important on a quadratic word problem, particularly the positive one. The positive one usually represents the value when your thing that's flying hits the ground. And if you look at the picture, it kind of makes sense as something being thrown into the air, the maximum height that it reached, and then when it actually hit the ground. So the x value will be the time that it hit the ground. Of course, the height when it hits the ground should be 0. On your y-axis, your height dropped down to 0. One more key feature before we actually work one. We'll look at the y-intercept. The y-intercept occurs where the x value or the time is 0. Okay, so sometimes that's an important part of the graph. A lot of times they'll call this value the starting point or the initial point or the initial height of whatever it is that's flying through the air, being thrown through the air, because that's when the time was 0. That's when we started. All right, let's actually do an example now. If a toy rocket is launched upward from the ground with an initial velocity of 128 feet per second, then its height after t seconds is given by the equation h of t, which is just function notation, equals negative 16t squared plus 128t. And we're neglecting air resistance. It says draw a general graph to model this. Now you can use your calculator, certainly. Just use the value for x in place of the t. And I'm going to draw a rough graph, just a generalized graph of what mine looks like on my calculator. Now this isn't perfect, of course, but this is just a general picture of my scenario. I'm going to go ahead and identify some of the key parts. Using my calculator, I found the maximum value, the vertex. The value of the vertex was 4,256. Notice how this graph is not drawn to scale. And I think another important value to go ahead and find are the roots or the x-intercepts. One of them is at 0, 0, so our starting point was at the ground. And I also need to go ahead and find the value of our other root, which is 8, 0. I think using this rough graph may help me answer most of the questions on the next slide. On this slide, we'll answer some questions about the quadratic that we've modeled. Keep in mind that the horizontal, or the x-axis in this case, is representing time, and the vertical, the y-axis, is representing the height. First question says, how long, implying time, will it take the rocket to reach its maximum height? Well, according to my model here, my maximum height, the vertex, is at 4,256. But if I want to know the time value, how long did it take, I've got to look along the time axis, or the x-axis. In this case, it looks like the correct answer is 4 seconds. All right, number 2 says, what is the maximum height? How high did the rocket actually get? That's going to be the y-axis, or the vertical axis. In our case, the highest point that this reached would be the y value of my vertex, which is 256 feet. Next question says, how many seconds until it hits the ground? So try to visualize this rocket being shot up in the air and then making its way to the ground. How many seconds, remember, is on the x-axis for time. So the x value of that point where it hits the ground is 8. So it took it 8 seconds to hit the ground. And the last example is a little tricky. It says, after how many seconds, so that's what I'm looking for, will the rocket be 112 feet above the ground? So I need to take this 112 value for feet, plug it in for the height. So that would be this part, this left part of my function up here needs to be made a 112. And then I'm going to bring down the values from my formula that should allow me to solve for the time. I want to solve this for the time. What time will the height be 112 feet according to this question? This is a quadratic. I like to graph to solve my quadratic, so I'm going to go ahead and put this in standard form by subtracting 112 from both sides. Now that my quadratic function here is about to be in standard form, which is negative 16t squared plus 128t minus 112 after I've moved over the 112, I'm going to graph it and find the roots. I found them to be at 1, 0 and 7, 0. And if you think about that for a second, that kind of makes sense. If we're looking for when the height was 112 feet, according to the question, and we started at 0, it's going to reach 112 feet on its way up, reach its maximum point of 256 feet, and then hit the 112 feet height again on its way down. So it looks like this rocket at 1 second and at 7 seconds will be at 112 feet high. So the answer to this one would be at 1 second and at 7 seconds. Those are the heights, those are the seconds, the amount of time that the rocket will be at 112 feet above the ground. All right, hope this helps, and thanks for watching.